For centuries, motion meant one thing: contact. Wheels were improved, modernized, and perfected. But no matter how advanced the wheel became, it still had to touch. And touch means friction. But what if we don't need wheel at all? In 1934, a German engineer, Hermann Kemper, imagined something extraordinary, a train that could float. Using magnetic force, he proposed contactless motion, eliminating friction entirely. It was a bold idea, far ahead of its time. But levitation alone was not enough. The train had to move. In 1950s and 60s, Eric Letwait made this idea possible. He took a conventional motor and unrolled it into a straight line. Instead of rotation, it produced linear motion. How did this help Maglev? Coils in the track are energized in sequence. This creates a moving magnetic field. The train's magnets interact with it. Result, the train is pushed forward continuously. By 1970s, world had one choice, not one solution, but two: EMS and EDS. In 1970, Germany adopted EMS, electromagnetic suspension, using the system Transrapid. The train didn't drive the track, it hugged it. The technology here is attraction-based levitation. EMS uses the attractive force between an iron core electromagnet and ferromagnetic rails. Electromagnets with current flowing through them are placed on the underside of the carriage, creating a magnetic field that is attracted to the opposite pole of the stationary ferromagnetic reaction rails installed on the underside of the guideway. This attraction results in a distance of just 1 millimeter between the stator and the support magnet, which allows the carriage to hover 150 millimeters above the top of the guideway. For propulsion, electromagnets are used. These are called propulsion coils. Many propulsion coils are arranged in series along both sides of the track. Power is supplied to those coils in such a way that if one coil acts as a north pole, the adjacent one acts as a south pole. In this way, alternating polarity is created along the track. Because electromagnet is a magnet, which polarity can be changed by controlling the current. So, we can reverse the north and south pole as needed. Now, it is very interesting to see how electromagnet of the train and ferromagnet of the train work together to propulse the train. Train is both pulled and pushed by a moving magnetic field. The track has electromagnetic coils along its length, which can be switched on and off in a controlled sequence. The coils on the track are activated in sequence. The coil ahead of the train becomes the opposite pole, attracting the train forward. The coil behind becomes the same pole, repelling the train forward. So the train is pushed and pulled at the same time. As the train moves, the magnetic field pattern moves along the track, continuously propelling the train forward. Meanwhile, in Japan, EDS was adopted, electrodynamic suspension. Here, superconducting magnets are used because in a magnetic levitation train, a very strong magnetic field is required. Stronger the magnetic field, better will be its propelling and lifting effect. Why are superconducting magnets used? Because there are limitations of electromagnets. When current flowing through a wire becomes too high, the wire heats up due to resistance and may get damaged. But this does not happen in case of superconducting magnets. The conductor is cooled below its critical temperature where its resistance becomes zero. As a result, a very high current can flow through it without energy loss. A superconducting magnet in this state produces a very strong and stable magnetic field. Here, propulsion happened with the same principle we discussed for EMS. As I said, along the track, coils are energized in sequence, creating a moving magnetic field. The train is pulled from the front and pushed from behind. If you want to understand this in detail, you can reverse back to the EMS system. For magnetic levitation, 8-shaped coils, also called null flask coils, are used. These coils are simply conducting loops and have no external power supply. Their working is based on Faraday's laws of electromagnetic induction, which states that a changing magnetic flux through a circuit induces an EMF on it. So when a conductor experiences a changing magnetic field, an EMF is induced. And if the circuit is closed, the current flows. Now let's apply to maglev. The superconducting magnets placed on both sides of the train together behave like a strong magnetic system. As the train moves forward, the magnetic flux through the 8-shaped coils changes. According to Faraday's law, this changing flux induces currents in the coils. According to the right-hand rule, the currents in the upper and lower loops of the 8-shaped coil flow in the opposite directions. These currents generate their own magnetic fields. As per the rule, a north pole is generated in the lower loop and a south pole is generated in the upper loop. Now, if you look carefully, these two north poles repel each other, due to which the train experiences an upward lift force. If this lift force is greater than the gravitational force, then the train will levitate. At low speeds, the change in magnetic flux is small, so the induced EMF and current are also small. Therefore, sufficient lift is not produced. That is why the train uses wheels during starting and stopping. As the speed increases, the induced current increases, the magnetic effect becomes stronger, and the train lifts off the track. At high speed, the wheels are retracted like an airplane. Now comes the final requirement, guidance. Train must remain centered to avoid touching the sides at high speed. For this, the 8-shaped coils on both sides are connected through the interconnecting coils. When the train is perfectly centered, equal EMF is induced on both sides, so no current flows through the connecting coils. But if the train shifts slightly to one side, the magnetic flux becomes unequal. This induces different EMFs in the coil, causing current to flow through the connecting coils. This current creates an imbalance in magnetic forces, producing a restraining force that pushes the train back towards the center. Once the train returns to the center, the EMFs become equal again. The current stops and the system stabilizes. In this way, propulsion, levitation and guidance all work together to move the maglev train at very high speed without any physical contact. In 1984, the world's first commercially operated maglev train opened in the United Kingdom at Birmingham using EMS technology. It was called the Birmingham Maglev at Birmingham Airport to Birmingham International Railway Station. Distance 600 meters, speed 42 kilometers per hour. This proved that maglev is not just a theory, it can work in real life. But unfortunately, it was shut down in 1995 because it had some flaws and it was slow compared to other modern maglev systems. The real turning point for modern maglev came with the Shanghai maglev train in Shanghai. In 2003, the trial run was completed. By 2004, it was ready for commercial operation. This became the world's first high-speed commercial maglev line. It connects Shanghai Pudong International Airport and Longyang Road Station. Length 30 kilometers, top speed 430 kilometers per hour, travel time 7 to 8 minutes. Technology used here was also EMS. And in April 2015, Japan set a historic milestone with its superconducting maglev system known as SCMaglev. Speed achieved 603 kilometers per hour. This became the fastest train speed ever recorded in the world. Technology used EDS, levitation gap 10 cm, much larger than the EMS system. No physical contact with the track, extremely stable at high speed. Why was 603 kilometers per hour possible compared to earlier systems? Because it has stronger magnetic fields, that is superconductors, larger gap, safer at high speed, less instability at high velocity, and ideal for ultra-high speed travel. Today, maglev represents the future of transportation, faster, smoother, and more efficient than ever before. And perhaps this is just the beginning, because once we know how to move without wheels, we are no longer bound to the ground. If you found this video interesting and informative, please hit a like, share, and subscribe. Bye-bye.